So this video marks the start of Chapter 8, and the first big topic in Chapter 8 is going to be on graphing exponential equations. This is a new kind of equation we haven't seen before, and this is the general form that you write an exponential equation in. This is called exponential because the variable, the x that we're going to be plugging in for, is actually in the exponent here. That hasn't happened before. So the variable for an exponential equation is in the exponent. That's what actually makes it exponential. A and B will generally be given to you, like I'll say going in what both of these are, but that variable that we're going to plug in for is right here. In this video, I'm just going to show you one example of an exponential equation we're going to graph, and I'm going to talk about what the graph looks like here. So for our example, I'm just going to use y equals 2 to the x power. That's an example of an exponential equation because, again, the variable is up here in the exponent. So what we're going to do to graph this is make a table. One thing before I get to that, in terms of this form right here, the b would be 2. We don't see a number out front right here, so if I was to write it in a times b to the x form, there'd be like a 1 right here that we don't see, obviously. So that's going to be our exponential form for this one. As I was just saying, we are going to graph this equation by making an input-output table with x and y. And we're just going to start plugging in numbers and see what the shape of our graph is. So I'm going to start out with just a 1 here. Actually, you know what? I'm going to start with 0. If I plug in a 0 for x, that means I have to do 1 times 2 to the 0 power. Remember, anything to the 0 power, I do my exponent first, this. Anything to the 0 power is just 1, and 1 times 1 is still a 1. So I'm going to graph 0, 1 from that point right there. I'm going to go ahead and plug in a 1, and I'm going to stop writing the 1 out front because it's not going to affect anything for this example. I'm going to do 2 to the first power. 2 to the first is 2, so I'm going to graph 1, 2. If I plug in a 2, 2 to the second power is going to be 4, so I'm going to graph 2, 1, 2, 3, 4. If I plug in a 3, 2 to the third is 8. And then I'm going to do one more point, because you'll see it'll go off the grid here. If I plug in a 4, 2 to the fourth power is going to be 16. So I'm already here off my grid if I was to do 4. One of the biggest features of exponential graphs that we're going to be talking about, they tend to grow faster than any other kind of graph we cover in Algebra 2. This graph is just going really high up into the sky here. It's just going to keep on going. And that is something that it grows faster than a quadratic, a cubic, any sort of equation we've had. After that, if I plugged in a 5, it would be 32. What's really happening is every time I go down one number, when I go up one number in the x's here, I'm doubling every single time. I'm multiplying by 2 to get to my next numbers. They're very, very steep. What I want to talk about here, though, is this part of the graph where you plug in negative numbers. So I'm going to add that in right here. If I plug in, for example, a negative 1, that means I have 2 to the negative first power, because I'm plugging in a negative 1 for x. 2 to the negative first power, if you guys remember, you send it to the bottom of the fraction. This is the same thing as 1 over 2 to the first, which is just 0.5. So if I plug in a negative 1 on this graph, I will get out a 0.5. If I plug in a negative 2 for x, 2 to the negative second power, send it to the bottom. It's going to be 1 over 2 to the second, which is 1 over 4, which equals 0.25. So it's going to be negative 2, 0.25 right there. I'm running out of space here, but I'm going to add in at least one more. If you plug in negative 3, 2 to the negative third, you send it to the bottom. It's going to be 1 over 2 to the positive third, which is 0.125. So it's negative 3, 0.125 there. If I plug in a negative 4, it's going to be 1 over 16, whatever the decimal is for that. Basically, even if I had, I'm out of room here, I'm going to plug in a negative 50 for x, continuing my table over here. If I plug in a negative 50, I have 2 to the negative 50th power. So I have to send it to the bottom of the fraction, turns into 1 over 2 to the 50th, which is going to be some crazy small decimal. It's still positive, it's just really, really tiny decimal. So I don't even know what it is. I don't have a calculator right here. I'm just going to write down tiny decimal here, because I don't even know what it is. So basically, what happens on this graph, if I continue this part, is it completely, or it very much flattens out along this side. It gets so close to 0 that it kind of looks like it just hits 0. But the graph is never actually going to get all the way to 0, because no matter what negative number you plug in, you're going to have 1 over a really big number. So the graph basically levels out right here. Totally flat on this side, it tails off, and it's really steep on the other side of the graph. That is what the basic shape of an exponential graph is. So anytime you see an equation with a variable and an exponent, it's going to be this kind of shape. Flat tail side, really steep side. Maybe it gets reflected so it's going this way or it's turned upside down. This is the shape of exponential graphs though. Couple things before I close out this video. I mentioned that the graph was kind of leveling out right here. It's getting flat. It's basically hitting 0 right here. That is a new vocab word you've probably never heard before. It's an important vocab word. I'm going to draw in a dotted line right here. It's kind of hard to see because I'm drawing it over my black line. But my graph levels off along the line right here, along that blue dotted line that you can kind of sort of see. That line is a special name called a horizontal. And the new vocab word here is called an asymptote. A-S-Y-M-P-T-O-T-E. Pronounced horizontal asymptote. It's a weird word. It basically refers to the value where your graph levels off, where it flattens out. None of the graphs we've talked about so far in Algebra 2 have had this, but it's the place where it levels off. So on your notes or whatever, somewhere in there, a horizontal asymptote is a y value that your graph eventually levels off to. And when you write this down, this definition isn't very official. Like, it's not precise like you would see in a math book, but it's the basic idea behind it. It's a y value that your graph eventually levels off to. Okay, so we would say that this graph, I'm going to do a few things with domain and range on this graph right here. I'm going to start out, though, with the horizontal asymptotes. I'm going to abbreviate that HA. This graph has a horizontal asymptote at y equals 0. It levels off completely at 0 here. So I'm going to put y equals 0. The domain of this graph is going to be all real numbers. It's going to keep going left indefinitely this way. It's going to keep on going. And even though it's really steep, it does keep going to the right. It's eventually going to hit all x's going right. So domain for exponentials, typical exponentials, is all real numbers. And our range on this one is the y's. Our y's that we hit on this graph will never go down here on this particular graph because it's leveling off right here. It's going to be from the asymptote, and it's going to be above for this one. So I would just say y is greater than 0. This time I will not put or equal to here, just greater than, because on this graph we never actually will hit 0. No matter what number you plug in for x, negative number, you're never going to actually reach 0. It gets rounded to 0, but it technically is a small positive number. Final thing I want to mention for this video, and then I'll close it out and start the next one. We have to often, we're asked to find intercepts on this graph. This graph, if you look for a y-intercept, definitely has one. There's a y-intercept right there at 0, 1. In terms of x-intercepts or roots, though, this graph does not have an x-intercept because it's not going to actually reach 0 there, so there would be none of that. All of these pieces of information are things I will ask you to do as we graph